Everybody, welcome back to the section 1.3 video looking at differential equations as mathematical models. So let's look at a couple more examples for this topic. So a very popular one and most common one is Newton's law of cooling and heating. Okay, so let's go ahead and look at the statement of Newton's law of cooling and heating, and then we'll develop the well-known mathematical model. So the rate at which the temperature of a body changes is proportional to the difference between the temperature of the body and the temperature of the surrounding median, which means ambient temperature. Okay, so much like before, we want to develop a variable and from there develop the derivative and any other elements that we need, like proportional or other types of constants. So we want to say T is the temperature of the body at time T. So temperature is, excuse me, T is the temperature of the body at time T. Okay, with respect to time. Okay, so that's our variable. And then we could kind of pick it apart from there. So the rate at which the temperature of a body changes. Okay, so we have our derivative now, dt over little t. So this is the rate of change of temperature. Okay, so the rate at which the temperature of a body changes is proportional. So we have another proportional constant here. Is the difference between the temperature of a body and the temperature of the surrounding median, which means ambient temperature. So that to me is also a constant. So what what is typically labeled as is capital T sub A, and that stands for ambient temperature at time T. And so we take this statement and now try to start writing the differential equation with all our components. What we would say here is that the rate at which the temperature of a body changes is proportional to the difference between the temperature of the body and the ambient temperature. So the difference, that means subtraction, right? So it would be K times the temperature of the body, T of T, minus the ambient temperature. And then, of course, we need an initial condition. So we'll just say at time zero, so T of zero, we have an initial temperature. And that is Newton's law of cooling. Okay. So let's go ahead and move on to the next application. That is spread of disease. Okay, so the rate at which a disease spreads is proportional to the number of interactions between those who are sick and those who are not sick. Okay, so this one's a little tougher to pick through, but let's go ahead and give it a shot. So what I want to say here is for our variable that we need to pick, we'll just use x for here. Okay. So we'll say x is the number of people with the disease. And we'll say n is the total size of this specific community that is being affected by this disease. And we also need to account for the number of people who don't have the disease. So what we would say is n minus x represents the number of people without disease. Okay, we have another proportional constant, k. So proportional constant. And we need to also account for interactions. And the way we would consider this based on the variables we have had before is x times n minus x is the interactions occurring. Okay, so number of people with disease times the number of people in the community minus the people with disease. So it's really just x times people who don't have the disease. Okay, so if we take all this, we want to write it as a differential equation, as an initial value problem. So what we will write is the rate at which a disease spreads is proportional to the number of interactions between those who are sick and those who are not sick. And I guess I maybe forgot to write the rate, but I think you guys can assume that. But yeah, so this is our differential equation. We need an initial condition, but really just need patient zero. So x of 0 equals 1, meaning like our patient 0. Okay, so this is our model for spread of disease, also well known, also used before. We're just breaking the statement apart and writing how we develop it. But okay, so that's it for section 1.3, differential equations as mathematical models, just a couple examples. We're going to look more of this uh, in detail in chapter 3. Okay, but here's just a brief introduction and just creating a differential equation. In chapter 3, we're actually going to apply these more. But that's it for this video, and I'll see you in the next one. Okay, take care.